Hello everyone, I am Ranmode from the Department of Computer Science Engineering, currently studying in TYB Tech in MIT Academy of Engineering, Arandi, Pune. So, today we are going to take an overview of optimization of loss function and best fit line using gradient descent. So now let's start with the basic. What is regression? Regression is a type of supervised learning technique used in machine learning and statistics. Its main goal is to predict a continuous output value based on one or more input variables. In simpler terms, regression helps us to find a relationship between things we know that are inputs and the things we want to predict that are outputs. So now let's see the basic regression equation. Y is equal to mx plus c. Here the y denotes predicted output, whatever we are trying to find. X denotes input variables, the known data. M denotes the slope, tells us how much y changes when x changes. It shows the strength and the direction of the relationship. C denotes the intercept, the value of y when x is equal to 0 where the line crosses the y-axis. So now let's understand the concept with an example based on predicting length based on price. Here we have taken two variables, one independent variable x which is price in rupees, and second one dependent variable y which is denoting length in meters. This data set will help us to analyze how length changes with the change in price of a wire. The main objective behind this is to predict the length of wire by its price. With the help of this simple real world example, we would get to know loss function and optimization. Here, we are able to see both the inputs in the tabular form, the price and the length. Here we can see a simple plotted graph where we, we have plotted the data as price on x-axis and length on y-axis. However, all these points don't lie in the same line. This is where actually the best fit line can help us to get the more accurate prediction. Here the data are uneven and not even in a single line. So, using regression, we can find an approximate line that fits our data best. In this example, our regression equation is y is equal to 0.2193x minus 9.1614. Here the slope m is 0.2193, meaning for every 1 rupee increase in price, the wire length increases by about 0.2193 meters. The intercept C is minus 9.1614, which represents the value of y when x is equal to 0. This line may not touch all points but gives us the best overall prediction. So now let's see in short what the best fit line e- exactly means. It's the line representing the relationship between input and output variables in most accurate way possible. The idea is to optimize the total distance or error between the actual data points and the line. Even though it doesn't pass through every single point, it's positioned such that the overall error is the smallest. The line helps us predict new values and understand the trend or correlation in our data. So now let's check the accuracy of the line and see the concept of loss function. Here we can see the line is not accurately passing through all the points. Here's the condition where the loss function comes into the play. The loss function is like a scorecard that tells us how well or poorly our regression model is performing. When we train a regression model, we are trying to draw a line or curve that best fits the data points. The loss function measures how far our model's predictions are from the actual values. It's essentially a measure of error. Common function mean squared error, which is one of the most common loss function. MSE, which calculates the average of square differences between predicted and actual values. A smaller MSE means a line is closer to data points and hence more accurate. Here we can see the formula J in bracket M comma C is equal to 1 upon N summation in bracket Y of I minus in bracket M xi plus C bracket complete square. Optimization. Once we know how to measure loss, the next step is optimization. Optimization is the process of finding the best values for our model parameters, mainly the slope m and intercept c, that will minimize the loss function. This helps our model learn and improve with each step. The most commonly used optimization technique is called gradient descent. Here we can see the graph of cost function showing the minimum point, which is situated between 0.200 and 0.225. Minimizing loss using gradient descent. It's an iterative algorithm of gradient descent that keeps on adjusting m and c to reduce the loss step by step. Imagine you are standing on top of a mountain. The loss function represents the mountain shape. Your goal is to reach the lowest point, which represents the minimum loss. So you take small steps in the direction of the steepest descent. That's how the algorithm moves towards the minimum. Each step improves the model's prediction until the loss becomes very small. That's when the model has to find the best fit line. Here you can see the steps 0, 1, 2, 3, 4, 5 going down the way to the lowest point. The parameter update rule is given by the formula m is equal to m minus alpha dou j upon dou m, c is equal to c minus alpha dou j upon dou c. At that point, the algorithm has reached the lowest possible loss, meaning it has found the best fitting line for the data. How gradient descent optimizes parameters. Let's see the step by step. Initially, for the first step, we will start with the random values of m and c. In second step, we will predict the prices using a formula y is equal to mx plus c. In third step, we will compute the loss, that's j. In fourth step, we will calculate the gradients dou j by dou m, comma, dou j by dou c, both one. In fifth step, we will update m and c using the update rules and the formula. In sixth step, we will repeat until repeat j until we get the minimum value. After multiple iterations, gradient descent reaches the minimum loss and gives the best fit line. Each iteration improves accuracy. The line slowly adjusts to reduce errors. Finally, we get the optimal best fit line. So now let's see learning rate. Learning rate, often represented by alpha, controls how big each step in the gradient descent process is while trying to reach the minimum loss. If alpha is too small, the algorithm moves very slowly. It takes many steps to reach the best point. If alpha is too large, it can overshoot the minimum, jumping back and forth, failing to settle, making learning unstable. A balanced learning rate helps the model learn smoothly and efficiently, reaching the global minimum in fewer steps. Usually, it's chosen through experimentations with common values like 0.01, 0.05, or zero point 0.1. Now we will see the real-life applications of gradient descent. Gradient descent is widely used in many real-world applications of machine learning and data science. It helps models learn by minimizing errors and improve accuracy over time. Some common uses include training neural networks used in deep learning to adjust millions of parameters efficiently, predicting house prices to find the best relationship between features like size, location, and price, financial forecasting for predicting stock trends, risk assessment, and pricing models, image recognition, optimizing models to correctly classify or detect objects in images, natural language processing (NLP), improving text prediction, translation, and sentiment analysis, autonomous systems, training self driven cars to make better navigation decisions. In short, gradient descent effectively discovered the optimal relationship between the wire price and length in our example also. The simple concept forms the foundation of machine learning, enabling the models to learn and make accurate predictions from the data. Conclusion: gradient descent plays a vital role in optimizing regression models by minimizing loss function to achieve the best fit line. Through repeated updates of parameters like slope m and intercept c, it continuously reduces prediction errors and enhances model accuracy. In the length of wire prediction example, gradient descent successfully discovered the optimal relationship between wire price and length, clearly showcasing its effective. Overall, this technique forms the foundation of modern machine learning and AI, enabling models to learn, adapt, and make accurate predictions from the data. That's all from me. Thank you.